Hello, and welcome to the Quantum Slumber, where we take big ideas from science and let them soften into something calm enough to fall asleep to. Tonight's question sounds almost too simple to be unsettling. Even if you took everything out of the universe, you still wouldn't have true emptiness. Not the kind of emptiness we imagine when we picture a blank room, or a silent stretch of space between stars. Physics has a stranger kind of nothing. A nothing that still has a background. A nothing that still has rules. And, in a quiet way, a nothing that still has motion. Because in modern physics, the universe isn't built out of little hard beads of matter floating through emptiness. Instead, it's closer to this. Space is filled with fields, invisible presences that can carry energy, store patterns, and ripple in specific ways. When those ripples appear in certain shapes, we give them familiar names like light, electrons, or particles. But underneath the labels, the deeper story is smoother and more continuous. And once you start thinking in fields, empty space stops being a lifeless stage. It becomes the stage and the music. So, if you're listening late tonight, you don't need to solve anything. You don't need to hold every term in your mind. Just let the ideas drift through at an easy pace. If you can, let your shoulders drop a little. Unclench your jaw. Take one slow breath in, and let it out as if you're setting down something heavy. And if you enjoy these slow journeys, if this kind of calm science helps you unwind, you can gently support the channel with a like or a subscribe. And I'd love to know, where are you listening from tonight? Just a city, a state, a country, whatever you feel like sharing. All right, let's begin as simply as we can, with the quietest question at the center of everything. What is a field? Before we answer that, it helps to slow down and ask an even gentler question. What do we mean when we say empty space? Imagine you walk into a room that's been completely cleared out. No furniture, no photos on the walls, no clutter in the corners, just open floor, quiet air, and that slightly echoing feeling that the space is empty. In everyday life, that's what we usually mean by nothing, an absence, a place where the usual things are missing. But physics is a little pickier with its words, because even that empty room is still full of something. Air molecules drifting, warmth leaking in from the walls, tiny vibrations traveling through the floor, faint radio signals passing through your body without you noticing. Even the light from a street lamp can slip under the curtain and scatter across the paint. Ordinary emptiness is really just not much stuff we care about right now. So, let's take the thought experiment further. Let's pretend we could do the impossible. We open the room and we remove the air itself. We pull every molecule out until there's no breath, no breeze, no scent, no dust. We cool it down until there's no leftover heat rippling around. We shield it from outside light. We isolate it from radio and sound. What's left? If you're like most people, your mind wants to land on a clean, blank answer, a perfect void, a pure nothing, a kind of cosmic silence. And classical physics, at least the older, simpler version, encourages that instinct. In that picture, vacuum is basically an empty stage. You can put things on it or not. You can remove the actors and the stage remains just unused. But modern physics slowly realized the stage isn't really empty, not even when the actors are gone. Because space isn't just a container where reality happens. Space has properties. Space can be stretched. Space can carry waves. Space can store patterns. Space can behave like more than a passive backdrop. And even before you get to the truly quantum part of tonight's story, there's already a clue hiding in plain sight. Light can cross empty space. If the space between the sun and Earth were truly nothing, light would have nothing to travel through, nothing to be as it moved. Yet sunlight arrives anyway, steady, reliable, obeying rules so strict we can build clocks and computers around them. Something about space allows those rules to exist, even where there's no matter. That something is where the idea of a vacuum begins to change. In physics, a vacuum doesn't mean the absence of everything. It means the absence of particles. No atoms drifting by, no electrons on the move, no little bits of matter you can point to and say, there's a thing. But the deeper story is that removing particles doesn't erase the underlying fabric that can produce them. On this is the gentle twist that can feel a little eerie the first time you sit with it. Even if you could take every particle out of a region of space, the region wouldn't become a blank nothing. It would still have structure. It would still have the capacity to do things. It would still be a kind of there with rules baked into it. Not a room full of objects, more like a quiet ocean before the wind arrives. No visible waves at first glance. No boats, no swimmers. And yet the surface is still a surface. The water is still water. The possibility of motion is still present, simply waiting. That's closer to what physicists mean when they talk about empty space. Not a dead void, but a background that can carry reality the way an ocean can carry ripples, whether or not ripples are currently passing through. And once you allow that idea in, the question changes. Instead of asking, how do we make nothing? You start asking, what is space made of if it can behave this way? And that's exactly where we're headed. Because the moment you stop thinking of vacuum as a blank absence, you naturally reach for a new word, one that means a value that exists everywhere, even when you can't see it. Something spread across space, quietly present, capable of influencing what happens. In other words, a field. So, let's start with the plain classical meaning of that word, gentle enough to hold in the mind before we add the word quantum. If the word field sounds technical, it helps to start with something your body already understands. Step outside on a mild day and you can feel it right away. Temperature isn't a thing you can point to, like a coin or a pebble, but it's still real. It surrounds you. It changes from place to place. It can be warmer near sunlit pavement and cooler under the shade of a tree. You can't hold temperature in your hand, yet it presses gently against your skin like an invisible weather. That's the basic mood of a field. A field is a way of describing something that has a value everywhere in space, not just here where you stand, but over there, and farther over there, and in the next room, and out across the town. It's like a quiet map that reality keeps drawing, even when no one is looking. Imagine a simple weather map on the evening news. It doesn't show you one single temperature. It shows you a whole landscape of temperatures, numbers spread across the state, changing gradually, sometimes sharply. A field is like that, except the map isn't ink on a screen. The map is the world itself. And once you see it that way, you start noticing fields everywhere. Wind is an easy one. You can stand still and feel air moving past your face. But the wind isn't the same in every spot. It's different at the corner of a building, different above a field, different between two houses. On a windy night, you can almost sense the air as a living pattern. Streams, swirls, pockets of calm, sudden gusts. If you wanted to describe that motion scientifically, you wouldn't describe it as one single wind. You'd describe a wind field, direction and speed at every point in space. The same goes for pressure in the atmosphere, or the humidity, or the density of fog. Even the smell of rain arriving early, stronger in one place, weaker in another, spreads like a gentle gradient across the neighborhood. None of these are objects, but they're all real because they do things. They can push, pull, warm, cool, carry, and change what happens next. That's the key test. A field isn't just a convenient story we tell ourselves. A field earns its place in physics because it has consequences. If you've ever felt a strong gust shove against your shoulder, you already believe in fields. Your body doesn't need equations to be convinced. Now, to make this idea feel even cleaner, imagine a long, empty stretch of road on a cool morning. The air is still. The only change is the temperature along the asphalt. Near the horizon, it's colder. Closer to you, it's warmer. There's no obvious boundary, no hard line, just a slow shift. If you could paint it, you'd get a smooth gradient, like a soft fade between two colors. That's a field too, a temperature field, quietly assigning a value to every point along the road. In physics, this way of thinking becomes powerful because it lets you describe nature without always tracking individual pieces of matter. Instead of chasing every molecule of air, you can describe the overall pattern, the average behavior spread across space. You trade a swarm of tiny details for a calm, continuous picture, and that calm picture turns out to be one of the most useful ways humans have ever learned to talk about reality. Because once you accept that something everywhere can be real, you're ready for one of the biggest leaps in science, the idea that forces can be fields too. A long time ago, people imagined forces like invisible ropes. The Earth pulls the moon with some kind of hidden tether. Magnets reach out and tug on each other like they're connected by ghostly strings. It's an understandable instinct. Our brains like contact, like pushes and pulls we can visualize. But fields offer a more peaceful picture. Instead of ropes, imagine influence spread across space. Not a single line, but a whole environment. A presence that fills the region and tells objects how to move if they happen to be there. That's why fields feel so natural once they click. They match the way reality often behaves, smooth, continuous, structured, and everywhere. So, when people say a field is like a map, that's not just a cute metaphor, it's almost literal. The world carries information at each point. Temperature here, wind speed there, pressure over there. And that information can flow, change, and interact. And here's the gentle step that starts steering us toward tonight's larger idea. Once physics got comfortable with fields, it became possible to look at something as familiar as light and ask a surprising question. What if light isn't just a stream of particles flying through empty space? What if light is a pattern in a field that already exists everywhere? Not a thing that travels through space like a bullet, but a ripple that moves across an invisible surface, something spread throughout the universe the way air is spread throughout a room. That question doesn't demand math yet. It just asks you to hold one quiet thought. Reality may have backgrounds that are not empty at all, backgrounds that carry values everywhere, and can be disturbed, shaped, and set into motion. And with that feeling in mind, it becomes much easier to meet the next idea. That light itself is tied to a field, an electromagnetic one, smooth and unseen, yet as real as wind against your skin. Light feels so ordinary that it's easy to forget how strange it is. It arrives without effort. It fills a room the moment a lamp is switched on. It slips through the gap beneath a door. It lays a pale rectangle across the floor, and then, as the evening moves, it quietly lifts that rectangle and carries it away. It can be warm on your skin, sharp in your eyes, gentle on a page. And for most of human history, that was the end of the story. Light was simply light. But physics eventually learned to ask a calmer, deeper question. If a field is something that exists everywhere, like a map of values spread across space, then what is light doing when it travels? Is it a stream of tiny pellets flying through emptiness? Or is it something more like a ripple moving through a background that's already there? This is where the electromagnetic field comes in. Instead of treating electricity and magnetism as separate mysteries, 19th century physics discovered that they behave like two sides of one continuous thing. A changing electric effect can create a magnetic effect. A changing magnetic effect can create an electric effect. They trade places the way two dancers trade steps, each one calling the other into motion. And when that back and forth happens in a self-sustaining way, when the electric and magnetic parts keep generating each other as they move, what you get is a traveling wave. That traveling wave is light. You don't have to picture it as a complicated diagram. You can picture it as a quiet, invisible surface that fills space, even where there's nothing else. When that surface is disturbed in a certain pattern, the disturbance doesn't just stay put. It moves outward, carrying energy and information with it, like a ripple crossing a pond, except the pond is everywhere. That's the electromagnetic field, a spread-out presence capable of holding patterns, capable of vibrating, capable of moving those vibrations across space. And once you look at it this way, a few everyday things start to feel a little more unified. Radio signals are not little objects racing through the air. They're slow, long ripples of the same electromagnetic field. Wi-Fi, Bluetooth, the signal that tells your car key to unlock the door. Same field, different kinds of waves. The warm hum of a microwave, the invisible reach of a cell tower, the soft glow of a nightlight. Different expressions of one underlying fabric. Even sunlight, which feels like the most natural thing in the world, becomes a kind of message. The sun shakes the electromagnetic field in a particular way. And 8 minutes later, the pattern arrives here, crossing 93 million miles of space without needing air, without needing wires, without needing a medium you can scoop up and hold. It's not traveling through space the way a fish travels through water. It's more like space itself is hosting the motion. That's the classical picture, and it's already beautiful. But there's an even subtler detail hiding inside it. When you say wave, your mind might imagine something that can be made arbitrarily small. A tiny ripple, a faint tremor. In classical physics, you can always turn the knob down. You can have less and less energy, smaller and smaller vibrations, until you're left with almost nothing at all. And for a while, that's exactly how people imagined light, as a continuous wave that could be made as gentle as you like. Then experiments began to whisper that reality doesn't always behave that smoothly. It was as if nature had a quiet preference for steps instead of slides. Light sometimes acts as though its energy comes in little packets, not because someone forced it to, not because our instruments are clumsy, but because that's how the electromagnetic field seems to behave when you look closely enough. You can dim a beam and dim it, and yet, when it interacts with matter, it often does so in discrete clicks, like raindrops landing on a roof rather than a perfectly even mist. That does not mean the wave picture was wrong. It means it wasn't the whole story. The wave is real, the field is real, and yet the exchange of energy can be quantized, delivered in distinct units. This is the doorway where electromagnetic field stops being just an elegant classical idea and starts leaning toward the quantum world. Because once you accept that light is an excitation of a field, once you accept that the field can carry traveling ripples, the next question becomes almost unavoidable. What happens when that field isn't allowed to vibrate with any amount of energy it wants? What happens when the universe insists on certain allowed amounts, like notes on a scale rather than a continuous slide? That's when the electromagnetic field begins to feel like more than a background for light. It begins to feel like a system with its own rules, rules that can turn smooth waves into countable events, like a melody turning into individual notes you can tap out, one by one. And if you let that idea settle gently for a moment, it leads to a surprisingly simple thought. Maybe light isn't a thing that travels through the universe. Maybe light is what the universe does when one of its fields is set into motion. And with that in mind, adding a single word, quantum, doesn't sound like a dramatic twist. It sounds like a careful next step, because we're not changing the subject. We're just changing the scale at which we're willing to look. Imagine you're watching a dimmer switch in a quiet room. You turn the knob, and the light seems to glide smoothly, brighter, softer, brighter again, like a continuous stream you can shape however you want. Your eyes accept that smoothness without question, because our everyday world is built out of things that feel adjustable, louder or quieter, warmer or cooler, faster or slower. It all feels like a sliding scale. For a long time, physics imagined light that way too. If light is a wave in the electromagnetic field, then it seems natural to think you can make that wave as gentle as you like. A smaller ripple, a quieter vibration. Turn the brightness down, and you should be able to drain the energy away in any amount, like pouring water from a glass. But when scientists began looking closely, really closely, something subtle showed up. Nature, it seemed, doesn't always do any amount. In certain situations, energy behaves less like a smooth ramp and more like a set of steps, not because reality is chunky in an obvious mechanical way, but because at the deepest level, the allowed patterns of a system can come in discrete notes. You already know this idea in a familiar form, even if you've never called it physics. Think of a guitar string. You can pluck it gently or hard, sure, But the string doesn't vibrate in just any shape it wants. It prefers specific patterns, standing waves that fit the length of the string, half a wave, a full wave, 1.5. Certain shapes fit and others don't. The string is free but not completely free. It has rules. Now, take that same feeling, allowed patterns, allowed notes, and apply it to energy itself. That's the quiet meaning of quantum. It doesn't mean tiny. It doesn't mean mystical. It means the system has built-in constraints, and those constraints can make energy show up in packets, little portions that can be counted, even if the underlying field is spread out and smooth. In the early days, this showed up as a puzzle tied to light and heat. Hot objects glow. They emit radiation. If you try to describe that glow using purely classical ideas, the math starts to misbehave in a way that's almost embarrassing. It predicts the wrong balance of colors. It predicts too much energy in the wrong places. It's like a theory insisting a piano can play infinitely high notes at full volume all at once, something the real world simply refuses to do. The fix was surprisingly simple in spirit. Energy isn't always exchanged continuously. In many cases, it is exchanged in discrete chunks, like paying with coins rather than shaving off microscopic slivers of a dollar bill. If the electromagnetic field can only hand energy over in certain packet sizes, then suddenly the world makes sense again. The glow of heated metal stops being a paradox. The spectrum of light coming from a warm object falls back into line with what we actually see. And then another, even more direct clue arrived. Shine light on a metal surface and, under the right conditions, electrons jump out. This is the photoelectric effect. The strange part isn't that electrons can be knocked loose. That feels reasonable. The strange part is how they respond. If light were purely a smooth wave, you might expect that a dim but high-frequency light would eventually build up enough energy, given time, to pop electrons out, like slowly pushing a swing higher and higher with gentle taps. But the electrons don't behave that way. Instead, what matters is the color, the frequency of the light. Below a certain threshold frequency, nothing happens, no matter how long you wait. Above it, electrons pop out quickly, and increasing brightness mostly increases how many electrons come out, not the kind of energy each electron seems to receive. It's as if the metal is not listening to a continuous whisper. It's listening for individual taps of a certain strength. That's the step-like behavior in action. Light can be spread out like a wave across space. Yet when it exchanges energy with matter, it often does so in discrete transactions. Each transaction has a size set by the frequency of the light. Higher frequency, larger packet. Lower frequency, smaller packet. This is where the word photon begins to feel less like a sci-fi label and more like a practical name for a real thing, an individual unit of energy in the electromagnetic field. Not a tiny marble, not a little bead with sharp edges. More like a single-counted note of excitation, one portion of the field's vibration that can be absorbed or emitted as a whole. And that's the gentle twist this section is trying to plant in your mind. The field picture and the particle picture aren't enemies. The electromagnetic field can support waves, flowing across space like ripples. But the field also behaves like a quantized system, one that trades energy in discrete amounts when it interacts with matter. A smooth ocean that, when you scoop it into a cup, arrives in individual droplets. Once that idea sinks in, the next move is almost unavoidable. If the electromagnetic field can be quantized, if its energy comes in steps, then it becomes natural to wonder whether every fundamental field has that same quiet staircase built into it. And if it does, then particles might not be the basic ingredients of reality after all. They might be the countable, step-like ways a deeper field can be excited. Which brings us very gently to an even stranger question, one that sounds like wordplay until you sit with it. If the field is always there, even when nothing is happening, what does nothing actually mean in a quantum world? When most people hear the word vacuum, they picture a kind of perfect emptiness, an erased blackboard of reality, No air, no dust, no sound, nothing moving, nothing happening. A silence so complete, it almost feels like an idea more than a place. And in everyday life, that definition works well enough. If you pump the air out of a jar, the jar is more empty than it was before. If you take away the smell, the humidity, the pressure, it feels like you're approaching a clean, pure void. But physics has a habit of taking our comfortable words and sharpening them. In classical physics, a vacuum is usually treated as a stage with the actors removed. You can clear the room, sweep the floor, lock the doors, and still have a room. The geometry remains. The background remains. You've removed the stuff, but not the place. Quantum field theory takes a quiet step beyond that. It says, even if you remove every particle you can name, every photon, every electron, every atom, you still haven't removed the underlying fields. And more than that, you haven't even found the most nothing state those fields can have. Because in quantum physics, vacuum isn't a location, it's a condition. A vacuum is a particular state of a system. And the particular state we mean, the one physicists care about, is the lowest energy state available, the ground state, the bottom rung the system can settle into when it has nothing left to give away. That sounds simple, almost restful. But here's the strange part. The lowest energy state is not the same thing as zero. In the classical world, you can imagine a pendulum hanging perfectly still. You can imagine a pond with no ripples at all. You can imagine a guitar string at rest. Motion can be fully turned off. Quantum mechanics is gentler and also more stubborn. It doesn't allow the universe to be pinned down into perfect stillness in quite the way classical intuition wants. Not because nature is chaotic, but because the rules of the quantum world place a limit on how perfectly certain a system can be, how precisely it can be both fixed and quiet at the same time. So, when we talk about a quantum vacuum, we're not talking about a universe that has been wiped clean. We're talking about a universe that has been allowed to settle into its most calm, most minimal configuration, while still obeying the rules of quantum uncertainty. It helps to think of it like this. Imagine a child spinning top. In a classical picture, you can slow it down until it stops. In a quantum picture, the top can't be made to have exactly zero motion in every meaningful sense. There is a baseline fuzz in what the system can do, and what you can say about it. Not dramatic, not noisy, just unavoidable. This is why physicists sometimes describe the vacuum as not empty, but that phrase can be misleading if it's heard the wrong way. It doesn't mean the vacuum is full of hidden particles like dust in a sunbeam. It means the fields are still there, and the fields still have a lowest energy condition that is not a dead, featureless zero. The vacuum is the fields in their calmest possible posture. For the electromagnetic field, the vacuum means no real photons traveling through, no light being carried from one place to another, no radiation flying by. And yet the field itself remains as a part of reality, like an instrument that is present in the orchestra, even when it isn't playing a clear, audible note. The important thing is that no photons is not the same thing as no electromagnetic field. Photons are the excitations, those countable units of energy we talked about a moment ago. They are the ripples you can name, the packets you can exchange, the clicks you can detect. The field is the deeper thing, the continuous presence that makes those ripples possible. So the vacuum isn't saying, the field is gone. The vacuum is saying, the field is as quiet as it can be, and no quieter. That little distinction, quiet as possible, not perfectly silent, turns out to matter in the real world, not just in philosophy. Because if the vacuum is the ground state, then the vacuum has structure, it has rules. It has a way of responding to being disturbed, and even a way of leaving faint fingerprints on the behavior of matter. That's why, later on, we'll be able to talk about effects that are measured in laboratories, tiny but real, where the vacuum seems to push back, or shift energy levels, or change what's allowed between objects. None of that requires you to imagine a storm of particles in empty space. All it requires is this calmer idea. A vacuum is not a blank page. It's the lowest energy page the book can open to. It's the fields present in their ground state. No obvious excitations, no traveling particles, yet still not a mathematical nothing. And once you see vacuum that way, a new question almost asks itself. If the vacuum is the ground state of a field, then what does that ground state actually do? What does it look like? Not to your eyes, but to the universe. Because in a quantum world, even the calmest state can have a kind of quiet motion inside it, so small you might miss it at first, but real enough to matter. And that brings us very gently to the next idea, the faint, restless background shimmer that can appear even in the emptiest space we can imagine. There's a moment, usually late at night, when empty feels like a real thing. A room goes quiet, the air seems to settle, even the smallest sounds feel far away, softened, as if the world is slowly turning its volume knob down. And if you imagine pushing that quietness farther and farther, removing air, removing light, removing heat, you might picture a kind of final stillness, a perfect blank. Quantum physics doesn't ruin that picture so much as it gently reshapes it. Because once you accept the idea that a vacuum is the lowest energy state of a field, a new thought follows almost automatically. If the vacuum is a state, then it still has rules. If the field still exists, then it still has the ability to move, at least a little. And if quantum uncertainty is real, then perfectly still becomes more like a classical wish than a quantum possibility. This is where the phrase quantum fluctuations enters the story. It's easy to hear that word, fluctuations, and imagine something loud, chaos, random fireworks in the dark, particles popping in and out like cartoon bubbles. But that isn't the vibe here. A better way to hold it in your mind is, the vacuum is calm, but it is not frozen. The ground state is restful, but it is not a perfectly flat line. It has a kind of built-in softness, like the faint, unavoidable trembling you might feel in your hand if you try to hold it completely motionless for a long time. Not because you're failing, because stillness has limits. In quantum mechanics, you can't specify every detail about a field with infinite precision. The field and its motion are linked in a way that doesn't allow both to be pinned down at once. The more tightly you try to lock one aspect into place, the less definite the other becomes. So even in the lowest energy condition, what we call the vacuum, the field retains a baseline restlessness, not an agitation, not a thing happening, just a subtle statistical shimmer in what the field can be from moment to moment. If you like imagery, picture a dark ocean at midnight. From far away, it looks smooth, almost like glass. But if you get close enough, you notice the surface is never truly flat. There are micro movements, tiny ripples, too small to count one by one, but real all the same. Quantum fluctuations are that kind of ripple, not on water, but in the values of the field itself. And here's a key point that keeps the whole idea from drifting into superstition. Fluctuations don't mean the vacuum is full of stuff in the ordinary sense. They mean the vacuum is alive with possibilities in a strictly physical, measurable way. The fields in their ground state still carry energy, minimal energy, but not zero, and they still respond to the basic quantum rule that nothing can be locked into an exact, perfectly featureless configuration. So, the vacuum isn't a dead void. It's more like a quiet baseline hum, so gentle you don't notice it directly, but present enough that, under the right circumstances, it can leave fingerprints. One reason physicists take this seriously is that the vacuum isn't the same everywhere once you change the environment. If you place boundaries in space, like metal plates close together, you're not just putting objects in an empty room. You're changing what kinds of field ripples are allowed to exist between them. You're changing the menu of possible fluctuations. And that sounds abstract until you let it sink in. The vacuum responds to constraints. The quiet has rules. The emptiness has preferences. It's as if the universe is saying, I can be as calm as possible. But if you reshape the space I live in, my calmness reshapes with it. That's why, later, we'll be able to talk about the Casimir effect, where two plates feel a tiny force because the vacuum between them is not the same vacuum outside them. Not because invisible particles are shoving the plates around like a prank, but because the baseline fluctuations, the allowed patterns of the field, are different in different regions, and nature always keeps score. Even before we get there, you can already feel the logic. Fields exist everywhere. A vacuum is a field in its lowest energy state. Quantum rules prevent that lowest energy state from being perfectly still in every sense. So the vacuum contains a faint, unavoidable kind of motion, quantum fluctuations. If you take nothing else from this section, take this. Quantum fluctuations are not the universe being busy in the way a crowded street is busy. They're the universe refusing to be perfectly silent in the way a classical equation might demand. A vacuum is quiet the way a sleeping house is quiet, not the way a universe erased to nothing would be quiet. And once you see fluctuations as the vacuum's subtle texture, it becomes much easier to understand the next step. Because if the vacuum can shimmer, then a particle, like a photon or an electron, doesn't need to be imagined as a tiny bead traveling through emptiness. It can be understood as something far more elegant, a localized, countable ripple, a clear little crest rising above the background. If quantum fluctuations are the faint texture of the vacuum, those tiny, unavoidable ripples in the background, then a natural question follows. When does a ripple become a thing? In everyday life, we're trained to think in objects, a pebble, a raindrop, a grain of sand, something with edges you could draw, something you could point to and say, that's it, that's the particle. But quantum field theory asks you to relax that instinct, gently, without forcing it. Because in this view, the most fundamental stuff of reality isn't a collection of tiny marbles flying through empty space. It's fields everywhere, and what we call a particle is not a separate object added on top of those fields. It's a particular kind of event in the field, an excitation, a localized, countable bump rising above the field's quiet baseline. Think of a perfectly still lake at night. Even in calm conditions, the surface has a faint shimmer, those subtle motions that never quite vanish. That's the background, the lowest energy state. Now imagine you tap the surface with a fingertip. A ripple spreads outward. It has a shape. It carries energy. It can travel. It can interact with other ripples. But it isn't a thing floating on top of the water. It is the water, moving in a particular pattern. That's the feeling you want for an excitation. A particle is what a field is doing when it's been disturbed in a specific quantized way. And that word, quantized, is the quiet magic here. In the classical world, you can tap the lake as gently or as strongly as you like, and the size of the ripple can vary smoothly. You can make a ripple that's half as big, or a third as big, or 1/1001 times as big. But in the quantum story, the field has allowed packets of excitation, certain discrete possibilities. The energy doesn't come in an infinitely sliding scale. It comes in steps, in countable units. So if you excite the electromagnetic field in the smallest allowed way, 1 unit, you don't get a bit of light. You get a photon, not as a tiny bullet, not as a miniature glowing bead, as the smallest indivisible unit of excitation of the electromagnetic field. And once you say that out loud, a lot of the weirdness starts to feel oddly clean, because it means the photon doesn't need to have a hard little surface or a hidden interior. It doesn't need to contain anything the way an object contains stuffing. It is a pattern in a field, a quantum of that pattern. The same goes for electrons, just with a different field. An electron is the smallest unit of excitation of the electron field. So the electron isn't fundamentally made of smaller pieces in this framework. It's the field doing its simplest, most particle-like act. And if you're thinking, okay, but why do we see particles as dots on a screen? Why do experiments look like little impacts? That's a good instinct, because the world often presents these excitations to us in a very particle-like way. When a photon is absorbed by an atom, the interaction happens in a discrete transfer, not half a photon, not a smeared out fraction, 1 quantum. When an electron hits a detector, the detector doesn't register a soft fog. It registers an event, a click, a point, a count. That's not a contradiction. It's the very signature of quantization. These excitations can spread out like waves while traveling, but when they exchange energy and momentum with matter, the exchange comes in whole units. So, the field picture doesn't remove the particle behavior. It explains where that behavior comes from. A particle is an excitation that is countable. You can count photons. You can count electrons. You can say 1, 2, 3. And yet the field underlying them is continuous across space, like a fabric that never breaks. This is why quantum field theory can sound so poetic without trying to be. Because it suggests the universe isn't built from tiny beads in a void. It's built from continuous fields, and the things we call particles are the smallest ripples those fields can carry, like notes on a string. A guitar string is one object, one continuous piece of matter, but when it vibrates, it can vibrate in modes, patterns, frequencies. In quantum fields, those patterns come with a rule. The energy of the vibration comes in discrete amounts. So, a photon is like a single note of the electromagnetic field, one quantum of vibration. An electron is like a single note of the electron field, one quantum of excitation with electron-like properties. And the properties matter here. Different fields have different personalities. The electromagnetic field's excitations behave like light. They carry energy and momentum in ways we recognize as radiation. The electron field's excitations behave like electrons. They have charge. They respond to electromagnetic forces in familiar ways. The identity of the particle is basically the identity of the field, which brings a strange kind of comfort. Instead of asking, what is a particle made of? You can ask, which field is being excited, and by how much? And that question scales beautifully. Because when you start to see particles as excitations, interactions become easier to picture too. Forces become fields talking to fields. Exchanges of excitations, patterns overlapping, interfering, canceling, reinforcing. The universe begins to feel less like a bag of billiard balls, and more like a vast continuous ocean where everything is a recognizable wave. And once you're holding that picture, one more phrase you've probably heard starts to make a little more sense, one that tends to confuse people the first time it shows up. Virtual particles, not as literal creatures flickering in and out like tiny ghosts, but as a way of describing how these excitations and interactions can be calculated, approximated, and understood when fields influence each other in the background. Not everything that helps you do the math needs to be a little object you could scoop up. Sometimes it's just the field's conversation, written in a language we can handle. The phrase virtual particle has a way of turning an otherwise calm idea into something spooky, like the universe is full of tiny ghosts, flickering into existence and vanishing again before anyone can catch them. That's a tempting mental image. It's also not the most helpful one. A gentler way to hold it is this. Virtual particles are often the language we use to describe how fields influence one another, especially when we're doing careful calculations. They're a way of keeping track of interactions, how energy and momentum can be passed around, without claiming that a little, fully formed particle literally popped into being and then died a moment later. Because in quantum field theory, forces don't have to be mysterious pushes across empty space. They can be understood as fields interacting. One field tugs on another, responds, and tugs back. And when we draw that interaction, we often draw it as an exchange. If you've ever seen a Feynman diagram, you know what I mean. Simple lines meeting, bending, connecting. The diagram looks almost like stick figure choreography. But it isn't a photograph of reality. It's closer to a shorthand note, an accountant's ledger, or a composer's score. It says, this is how the math is organized. So, when you hear a force is carried by virtual particles, it's often pointing to a specific idea. In calculations, an interaction can be represented as if something was exchanged between excitations of fields. Take the electromagnetic force. Two electrons repel each other. There's no tiny rod between them, no visible thread. Yet the repulsion is steady and real. In the field picture, each electron is an excitation of the electron field, and each carries electric charge, meaning it couples to the electromagnetic field. The electromagnetic field responds to that charge, and that response influences other charge excitations. When physicists calculate that influence, they often describe it as an exchange of virtual photons. And that's where the confusion begins, because photons are real things we associate with light: sunlight, lamplight, starlight. But a virtual photon isn't a little flash of light you could catch with a detector. It isn't something that travels out into the room like a beam. It's not a real photon, but faster. It's a bookkeeping object that appears inside the mathematical description of how the electromagnetic field mediates an interaction. A real photon is an on-the-books excitation you can detect as a discrete event. It carries a clean, measurable relationship between its energy and its frequency. It can move freely through space and eventually be absorbed, leaving a clear signature. Virtual photons, in contrast, are internal messengers inside the calculation. They don't have to obey the same neat relationship that real, detectable photons obey. They aren't required to show up as free, countable particles at the end of an experiment. They live in the middle of the story, not as a chapter you can pull out and read on its own. It's a bit like this. Imagine you're trying to describe a conversation between two people across a room. You could write the final outcome. One person changed their mind. The other offered a reason. Something shifted. But if you want to explain how it happened, you might sketch the exchange. Questions, pauses, responses, small clarifications, little misunderstandings corrected along the way. Some of those steps would never be detected by an outsider as separate physical objects. They're not independent things. They're part of the process. Virtual particles are like that, a way of representing intermediate steps in how fields interact. Now, none of this is meant to make them feel fake. The effects associated with these internal exchanges are real. Electrons really repel, magnets really pull, atoms really shift energy levels in tiny, measurable ways. The predictions that come out of this bookkeeping are often unbelievably accurate. What's virtual is not the reality of the interaction. What's virtual is the idea that the exchange must be pictured as a literal stream of tiny, freestanding particles popping in and out of existence the way a cartoon would show it. There's another common phrase people repeat here. They borrow energy from the vacuum. You'll hear it said as if the universe is handing out microloans. Energy borrowed for a moment, then paid back before anyone notices. It's a colorful story, and it points towards something real about quantum uncertainty. But taken too literally, it creates more fog than clarity. Because quantum field theory doesn't require you to imagine the vacuum as a bank account being dipped into. It's enough to know that the theory allows intermediate states and calculations that don't look like the final, measurable particles we detect. The mathematics includes contributions that are not directly observable as separate events, and yet they shape the probabilities and outcomes we do observe. So if you'd like a calmer definition you can carry without strain, it might be this. Virtual particles are a convenient way to describe how fields interact in the quantum world, especially in the middle of an interaction, without claiming those particles are independent, detectable objects. And once you accept that, something else becomes easier to accept too. Because if interactions have this soft, probabilistic structure, if the universe allows intermediate possibilities that don't show up as clean little objects, then it starts to make sense that there's a deeper principle underneath it all. A principle that isn't about messy instruments or imperfect measurements. A principle about the world itself, having built-in limits on what can be sharply defined at once. That quiet principle is what people usually mean when they say uncertainty. Uncertainty is one of those words that sounds like a human problem. Like we're unsure because we don't have enough information, because our tools are imperfect, because we're standing too far away, squinting into the dark, trying to guess what's really there. But in quantum physics, the strange twist is this. Uncertainty isn't mainly about ignorance. It's not the universe saying, you'd know the answer if your microscope were better. It's the universe saying very quietly, There isn't a single sharp answer to know, not in the way we're used to. To feel what that means, it helps to notice how our everyday intuition is built. We grow up believing that objects simply have properties. A ball has a position, a car has a speed, a cup is on the table, not sort of on the table. Even if you don't know the exact numbers, you assume the numbers exist, waiting patiently for you to measure them. Quantum mechanics doesn't remove measurement. It removes a certain kind of certainty that classical thinking takes for granted. And it does it in a surprisingly gentle way, by changing what properties mean at the smallest scales. A classic example is position and momentum. Position feels simple, where something is. Momentum is basically motion with weight behind it, how hard it would be to stop, how much going it contains. In everyday life, you can know both at once. You know where the car is and how fast it's moving. You can pin down both as tightly as you like, as long as you have good enough instruments. But in quantum physics, those two pieces of information aren't just hard to gather at the same time. They're woven together in a way that makes perfect sharpness impossible. It's not because the particle is hiding from you. It's because the state of the system can't be arranged to make both of those things perfectly definite at once. A calmer way to picture it is to think of a wave. A wave that's spread out over space doesn't have a single clean here. It's smeared. It occupies a region. But that spread out wave has a very clean, definite rhythm. It has a smooth, well-defined wavelength. And wavelength is tied to momentum. Now imagine you try to force that wave into a sharp location, like squeezing a long ribbon into a tiny knot. The tighter you squeeze, the less clean the rhythm becomes. The wave now requires a messy mix of wavelengths to build that sharp knot. That mix means momentum becomes less definite. So, uncertainty is not a punishment. It's not the universe being difficult. It's a simple consequence of what quantum states are. They aren't tiny marbles with hidden labels. They're closer to patterns that can be shaped, but not shaped arbitrarily. And that brings us to the other common misunderstanding, the idea that uncertainty is caused by the act of measuring. You'll often hear a story like this. When you measure position, you disturb the particle, so you can't know its momentum. That story isn't completely useless. It's true that measurement involves interaction, and interactions can change things. But it's not the heart of the matter. Even in a world with perfect, gentle, magical measuring devices, the uncertainty principle would still stand. Because it's not about the clumsiness of measurement. It's about the structure of quantum reality, about which kinds of information can be simultaneously sharp in a single physical state. If you want another image, one that stays soft and human, imagine trying to hold a handful of water. If your fingers are open, the water sits calmly in your palm and you can feel its weight and flow. But you can't hold it in a precise shape. If you squeeze your hand tight to define a shape, the water responds by slipping, shifting, escaping through the smallest openings. The more you demand a crisp boundary in one sense, the more the other sense becomes fluid. Not because the water is being tricky, because it's water. In that metaphor, uncertainty is simply the watery nature of quantum states. And once you accept that, the rest of quantum field theory starts to feel less like a collection of weird exceptions, and more like a consistent world with its own rules. Virtual particles are a way we organize interactions. Uncertainty is part of why those interactions can't always be pictured as clean, classical events. And the vacuum, what we casually call empty space, begins to sound less like a silent void and more like a stage where the rules of quantum patterns always apply. Because if uncertainty is truly built in, then even a field in its quietest possible state can never be perfectly still. There's always a kind of baseline softness, a faint restlessness, not loud, not chaotic, just enough to remind you that nothing is not the same as perfect silence. And in the next idea, that subtle restlessness leaves a footprint you can actually measure, something small, delicate, but real. If the vacuum is never perfectly still, you might wonder whether that restlessness is only a poetic idea, a nice story to tell at night, a metaphor that sounds comforting but evaporates the moment you ask for proof. And that's where the Casimir effect steps in, quietly, almost shyly, as one of the rare moments in quantum physics where something that feels philosophical becomes something you can, in principle, measure. Not in the sense of holding it in your hand. More like noticing a gentle pressure you didn't expect in a place you thought would be completely calm. Here's the setup, as simply as possible. Imagine two uncharged metal plates, flat, clean, parallel. They're placed extremely close together, so close that the gap is thinner than a human hair, thinner than dust, closer to the scale where empty space starts to feel like a physical environment rather than a blank stage. Now, if you were raised on the everyday meaning of emptiness, you'd predict nothing interesting happens between those plates. No magnets, no static charge, no air pressure difference if the air is pumped out. So, nothing. But quantum fields don't quite allow nothing to be featureless. Because in quantum field theory, a field isn't only something that appears when a particle is present. A field is there even when it's in its lowest energy state, its ground state, what we loosely call the vacuum. And even in that quietest state, the field behaves more like a soft, living pattern than like a switched-off machine. One way to picture that pattern is to think in terms of vibrations, loud notes that a field can hum, even when no one is playing a melody. That word aloud matters, because the Casimir effect is really a story about how boundaries change what's allowed. A simple familiar analogy is a guitar string. A guitar string doesn't vibrate with just any shape. The ends are fixed, so the string can only form certain standing waves, certain harmonics. You can pluck it, but the geometry of the string decides which notes are possible. Now, replace the guitar string with a quantum field, and replace the fixed ends with metal plates. The space between the plates becomes a kind of instrument, an unusually quiet one, where only certain patterns of the electromagnetic field can fit. If the gap is small enough, long wavelength modes don't have room to exist between the plates. They're excluded, the way a long, gentle wave can't form inside a tiny cup. Outside the plates, though, the field isn't constrained in the same way. There's more room, more freedom, more possible modes. So you end up with a subtle imbalance. Not an imbalance of particles flying around. An imbalance in the spectrum of possible vacuum fluctuations. And when the set of allowed modes differs between two regions of space, the vacuum energy differs too, by an amount that can produce a force. A tiny force, but a real one. The plates experience an attraction, as if the pressure from vacuum fluctuations outside is ever so slightly greater than the pressure inside. That's one intuitive story, and it gets the right feeling. The vacuum isn't just empty, it has structure, and boundaries can shape that structure. There's a second story that's also helpful, especially if you like thinking in terms of fields communicating with matter. Conducting plates respond to electromagnetic fields. They enforce certain conditions on how the field behaves at their surfaces. In doing so, they modify the field's ground state around them. And that modified ground state comes with an energy cost, an energy that depends on plate separation. When systems prefer lower energy, you can often translate that preference into a force, a gentle push toward the configuration that minimizes energy. Again, the details can get mathematical fast, but the emotional core stays simple. Change the geometry of empty space, and you change what empty means. What makes the Casimir effect so satisfying, especially in a slow, bedtime kind of way, is that it doesn't demand belief in anything mystical. It doesn't say the vacuum is a magic reservoir you can tap like a cosmic battery. It doesn't claim particles are popping in and out like cartoon fireflies. It's more restrained than that. It says quantum fields are real. Their ground states have measurable consequences. And when you put boundaries in space, you alter those consequences. Historically, this idea was sharpened into a prediction in the late 1940s by Hendrik Casimir, working with the behavior of conducting plates and the electromagnetic field. The attraction is incredibly small, so it took careful experiments, especially later, with improved surface preparation and precision measurement, to study it cleanly. And even then, the real world adds gentle complications. Surfaces aren't perfectly smooth, plates aren't perfectly parallel, Residual charges can sneak in, temperature can matter, materials aren't ideal conductors at all frequencies. So, when people measure the Casimir force, they do something very human. They patiently subtract the ordinary effects, isolate the subtle one, and check whether what remains matches the shape of the quantum prediction. And over time it has. Not because the vacuum is dramatic, because it's consistent. Now, if you're listening with half-closed eyes, you might be wondering, what should you take away from all this? You don't need to remember names, dates, or technical vocabulary. Just keep one clean picture. Two ordinary objects brought close together feel a tiny attraction. Not because of hidden magnets or static charge, but because empty space between them is not the same as empty space outside them. The vacuum is not a blank zero. It's a physical state with rules. And when you change the rules by changing the boundaries, you change the outcome. There's also a gentle lesson here about how quantum field theory often works. It doesn't always announce itself with fireworks. Sometimes it shows up as a slight shift, a faint pressure, a barely measurable nudge that you only notice when you create the right conditions. And that's exactly why this effect is such a perfect bridge into the next idea. Because the Casimir force is not the only place where the vacuum leaves fingerprints. In fact, one of the most delicate fingerprints shows up not between metal plates, but inside atoms, where the notes available to a field can subtly reshape the energies of electrons. Not by much, just enough to prove, again, that even the quietest background in nature is doing something. And that tiny, almost clock-like deviation has a name of its own, one that sounds like a whisper in a laboratory: the Lamb shift. If the Casimir effect feels like the vacuum pushing in a way you can almost sense, the Lamb shift is the vacuum whispering, so softly that you only notice it when you listen with the most careful instruments physics has ever built. It begins in a place that seems, at first, perfectly orderly: an atom. In the simplest picture, an atom is a tiny solar system, a nucleus in the center, an electron orbiting around it. That image is comforting, but it's also misleading. In quantum mechanics, the electron isn't a little planet tracing a neat path. It's described by a cloud of probability, an electron wave, spread out in space with certain allowed energies. Those allowed energies are like rungs on a ladder. The electron can stand on one rung or another, but it can't hover in between. And for a long time, physicists believed they understood those rungs extremely well. For hydrogen, the simplest atom with a single proton and a single electron, the rules seemed clean and almost elegant. You could calculate the energy levels, predict the frequencies of light hydrogen would absorb or emit, and match them to what you saw in the lab. Hydrogen became a kind of quiet proving ground for theories. If your math could predict hydrogen, your theory had teeth. But then the measurements became sharper, and the sharper they became, the stranger the story got. There were energy levels that should have been exactly the same, degenerate as physicists say, yet in real experiments, they weren't. The difference was small, almost embarrassingly small. Not the kind of thing you'd notice with a casual glance at a spectrum, more like a clock that loses a fraction of a second over many days. At first, that kind of discrepancy feels like a mistake, a dirty instrument, a stray electric field in the room, a human error in the analysis, a flaw in the assumptions. But it didn't go away. It persisted stubbornly across careful work, and eventually it gained a name: the Lamb shift, after Willis Lamb, who measured this tiny separation in hydrogen's energy levels in the late 1940s. So, what is it in plain bedtime language? It's a subtle change in the electron's energy caused by the fact that the electron is never truly alone with the nucleus. Even in a vacuum, even when you've cooled things down, shielded the environment, and done everything you can to silence the outside world, because the electromagnetic field is still there. And in quantum field theory, that field has a ground state, its quietest possible condition that is not perfectly flat. That quiet field can still fluctuate. Not in a way that shoots sparks across your room, but in a way that slightly changes the rules of the electron's environment. And when the environment changes, even gently, the allowed energy levels shift. One helpful image is to imagine the electron as a soft, spread-out presence around the nucleus, like a fog rather than a bead. Some electron states spend more of their time closer to the nucleus. Some keep their fog more distant. In particular, there are states, called S states, that have a non-zero probability of being right near the nucleus itself. Now, the electromagnetic field fluctuations interact with the electron. You can think of it as the electron constantly feeling a jittery background, an ever-present ultra-fine texture to space. This affects how the electron moves and how it sees the electric pull of the proton. But here's the key. Different electron states sample that jittery background differently. If a state spends more time near the nucleus, closer to where the electric field is strongest and changes most rapidly, then the quantum corrections to its energy can be slightly different than for a state that stays a bit farther out. So, levels that look identical in a simpler theory split apart when you include the deeper reality of the quantum field. That's the Lamb shift, a tiny lifting of a tie that you thought nature had declared permanent. There's another way to tell the same story, equally gentle. In quantum electrodynamics, QED, the quantum theory of the electromagnetic field, the electron is not just a point with a charge. It is also tied to the field it interacts with, and the vacuum itself contributes. The electron's properties, as measured, include the influence of its interaction with the field at different scales. So, what looks like a clean hydrogen atom is, in a deeper sense, a hydrogen atom plus a living electromagnetic vacuum, one that slightly modifies the electron's energy through what physicists call radiative corrections. You don't need that phrase. What matters is the feeling. The vacuum is not a blank backdrop. It participates. And the evidence isn't only in the space between plates. It's written into the fine print of atomic spectra. Why does this matter, besides being a beautiful detail? Because the Lamb shift was one of the great confirmations that quantum field theory wasn't just clever bookkeeping. It was describing something real. If your theory claims the vacuum has structure, you should see that structure show up somewhere. And hydrogen, simple, disciplined, and measurable, turned out to be one of the places where it does. It's also a reminder of how physics advances. Not always by dramatic overturning, sometimes by a small mismatch. A careful measurement that refuses to agree. A tiny crack in a perfect prediction that leads to a deeper understanding. And in a sleepy way, it's almost comforting. It suggests the universe has layers. That reality isn't exhausted by the first clean explanation we learn. There's always a finer texture underneath, waiting for patient attention. So, when you hear vacuum fluctuations, you don't have to imagine chaos. You can imagine something much quieter. A background hum so faint that it only reveals itself by nudging an electron's energy by the tiniest amount. A whisper in the spectrum. And once you accept that whispers can be real, the next challenge becomes clear. Because when physicists tried to calculate these tiny effects in full detail, across all possible scales, they sometimes found numbers that blew up toward infinity. Not because nature is infinite in a messy way, but because our descriptions needed a careful kind of cleaning, a way to renormalize what we mean by the measurable quantities in the first place. Sometimes the strangest thing about quantum field theory isn't the weirdness you can picture. It's the weirdness you can't picture at all, because the math, if you let it run freely, starts to shout numbers that don't seem to belong to reality. Numbers that grow without limit. Not very large. Not hard to measure. Just infinite. And that's usually the moment people lean back and think, okay, this can't be right. But renormalization is the reason physicists didn't walk away. It's the reason the theory became one of the most accurate things humans have ever written down. And the simplest way to approach it tonight is not as a trick, but as a kind of cleaning, a careful agreement between what we calculate and what we can actually observe. Imagine you're looking at a city at night. From a plane, it's a soft glow. Highways like dim threads, neighborhoods like warm patches. It's calm, readable. But now imagine you zoom in, closer and closer. Suddenly, the glow breaks into streetlights. then into individual bulbs, then into the tiny grains of glass, dust, and scratches on the lens you're using to look. At some point, the city isn't what's dominating your view anymore. Your zoom is, your instrument is, your perspective. In physics, that idea shows up everywhere. What you measure depends on the scale at which you look. Renormalization begins with that humble thought. Because quantum fields don't just live at one scale, they live at all scales at once. A field can ripple gently across a room, and also jitter at distances so small you'd need new language to even describe them. When we do calculations in quantum field theory, we often have to account for contributions from fluctuations at many different sizes, long, slow waves, and tiny, frantic ones. And if you try to include every possible tiny fluctuation without any guardrails, the bookkeeping can explode, the sums blow up, you get infinities. But here's the quiet twist. Those infinities usually aren't telling you that nature is infinite. They're telling you that you've asked the wrong question in the wrong way. Because we never measure the bare numbers the math starts with. We never hold a naked electron in our hands and read its true mass like a label on a box. We measure electrons through experiments, through interactions, fields, detectors, and the world in between. So what we call the mass of the electron, or the charge of the electron, is already an observed quantity, one that includes the influence of the surrounding quantum fields. The vacuum isn't a silent stage, it's part of the performance. So renormalization says something like this. Let's stop pretending we can separate the actor from the theater. Let's define our basic numbers, mass, charge, coupling strength, not as abstract, unreachable, true values, right? But as the values that match what we actually measure at a particular scale. In other words, we anchor the theory to reality. We pick a reference point, a certain experimental setup, a certain energy range, a certain zoom level, and we demand that the theory reproduce the measured results there. Then, with that anchor in place, we let the theory tell us how things change as we zoom in or out. This is where that Lao Keen, wiping the glass, image fits so nicely. When you wipe a window, you're not changing the world outside. You're removing the smudges that were confusing your view. Renormalization is like removing smudges that come from treating the math too literally at scales, where our simplified model isn't meant to be trusted. Because there's another truth hiding in the background. Every theory has a domain where it works. Newton's laws are brilliant, until you're near the speed of light. Classical electromagnetism is beautiful, until you're dealing with single quanta of light. And quantum field theory, as we use it, is astonishingly accurate. But we still expect that at some extreme scale, new physics may appear. So, when a calculation diverges, it can be a gentle hint that you're pushing beyond the range where the naive version of the theory should be taken as a literal description. Renormalization handles this by introducing the idea of a cutoff, an acknowledgement that, past some tiny scale, you don't keep blindly adding contributions as though your model is complete. Instead, you treat the unknown small-scale details as something absorbed into a few measurable parameters. And then you proceed. It sounds almost philosophical, but it's also extremely practical. Because once you renormalize, once you rewrite the theory in terms of measured physical quantities, you can make predictions that match experiments to an absurd number of decimal places. The magnetic moment of the electron, for example, is predicted so precisely that it's often used as a showpiece for the power of QED, not because physicists enjoy flexing, but because it reveals something profound. A theory can be built not on pretending we know everything, but on carefully admitting what we don't know and still extracting reliable truths from what we can measure. There's a soft, sleepy beauty in that. Renormalization is a reminder that reality is layered. That what something is depends on how closely you look. That the universe has a way of changing its face when you change your magnification, without ever becoming inconsistent. So if you ever hear that renormalization is sweeping infinities under the rug, you can hold a calmer picture. It's more like calibrating your compass, or adjusting your focus, or cleaning a lens so the stars stop bleeding into halos, and you can see the sky as it truly is. And once you accept that physics depends on scale, another idea starts to feel almost inevitable. If scale matters so much, then symmetry matters too. Because symmetries are the quiet rules that stay steady, even as you zoom in and out, keeping the whole strange structure from falling apart. There's a moment in physics when the mood changes. After the infinities are tamed, after the lens is cleaned, after the theory has been anchored to what we can truly measure, you start to notice something quieter, holding the whole structure together. Not a single equation, not a single particle. A preference, almost like a habit of nature. The universe seems to like rules that don't change when you change your point of view. That idea is what physicists mean by symmetry. And despite how fancy the word can sound, the feeling of it is familiar. You've known symmetry long before you knew the name. Think of a simple snowflake, or the face of a calm lake at night. Turn it slightly in your mind, and in a certain sense, it's still the same. Or imagine walking around a statue in a museum. From different angles, it looks different, but the statue itself hasn't changed. You changed where you stand. That's the heart of symmetry. Some transformation you can perform, some shift in perspective you can make, and the underlying truth stays the same. In physics, that becomes incredibly powerful. Because the world is messy, motion is complicated, fields ripple, particles appear, interactions overlap. If you tried to describe everything with no guiding principles, you'd drown in the details. Symmetry is one of the reasons we don't drown. It's like a set of quiet constraints that say, however wild things get, they still have to obey this. One of the gentlest symmetries to picture is translation symmetry, the idea that the laws of physics don't depend on where you are. If you run an experiment in your kitchen and someone runs the same experiment in a lab across town, or on a mountaintop, or in a desert, the core laws shouldn't care about the zip code. The results can change because of temperature, pressure, equipment, and noise. But the deep rules underneath remain. That simple fairness, physics working the same here as it does there, is not just comforting, it's productive. Because it implies something stable about the universe. The world isn't a patchwork of different rule books stitched together. It's one rule book, read in different places. Then there's rotation symmetry, the idea that the laws don't change when you rotate your entire setup. If you build an apparatus and turn it 90 degrees, the rules shouldn't suddenly act offended. Again, the details can shift, gravity, friction, nearby fields. But the underlying framework remains the same. Even time symmetry plays a role. In many situations, the laws don't care what day it is. You can repeat an experiment tomorrow, and, in principle, the same equations still apply. Time moves forward, sure, but the basic grammar of physics stays stable. Now here's where the story becomes almost magical, in a way that's quietly mathematical, but easy to appreciate. When nature has these symmetries, it often rewards them with conservation laws. This is one of the most beautiful connections in all of science. It's so deep that physicists treat it as a guiding lantern. Very gently, the idea is this. If the laws don't change from place to place, then momentum is conserved. If the laws don't change from time to time, then energy is conserved. If the laws don't change when you rotate things, then angular momentum is conserved. You don't have to memorize that tonight. Just notice the mood of it. Symmetry isn't only about prettiness or balance. It's a promise that something will not drift away, that something will remain steady, even as the world shifts and swirls. And that's why symmetry keeps the law, as you put it. It's like the universe's way of maintaining order without needing a supervisor. In quantum field theory, this becomes even more important, because QFT is a framework where you're constantly summing over possibilities. You're accounting for influences you can't see directly. You're letting fields hum at many scales, and you're carefully keeping track. Without symmetries, the number of allowed terms in the theory would explode. Anything could couple to anything. Predictions would become mush. But symmetries act like guardians at the gate. They tell you what's allowed and what's forbidden. They protect certain quantities from changing too much. They keep the theory from turning into an anything-goes dream. And there's another subtle role symmetry plays. It helps explain why some things remain small or stable, or consistent across different energy scales, especially after renormalization has done its work. Renormalization, in a sense, is the art of zooming. Symmetry is the rule that says, when you zoom, some relationships should remain intact. Some patterns should survive the change of magnification. Sometimes symmetries are exact, sometimes they're approximate, sometimes they're hidden until you look the right way. And sometimes, very importantly, they can be broken. A broken symmetry doesn't mean the laws stop being true. It often means the laws are true, but the system chooses a particular state that doesn't display the full symmetry. Like a perfectly round pencil balanced on its tip, symmetric in every direction until it falls. The laws were symmetric. The outcome picks a direction. That kind of symmetry breaking will matter later, when we talk about how the world can look rich and structured, even if the underlying laws are elegantly simple. But for now, let symmetry be what it is in this moment. A calm principle. A way the universe stays consistent as you shift your perspective. And from this quiet consistency comes one of the most intriguing ideas in modern physics. An idea that sounds almost like a secret handshake among equations. Because there is a form of symmetry that doesn't just involve rotating or moving your apparatus. It involves changing something under the hood, locally, point by point in space and time, and discovering that the demand for that symmetry creates what we experience as forces. And that is where the word gauge begins to appear. A useful way to meet a gauge field for the first time is to forget the word gauge for a moment and just notice something simple. Sometimes nature doesn't care what label you put on a thing, as long as your labeling is consistent. Think of temperature on a weather map. The air doesn't care whether you write the numbers in Fahrenheit or Celsius. Those are human choices. Or think of sea level. You can choose a zero height that feels convenient, but the mountains don't change just because you change your reference point. In physics, those choices, what you call zero, what direction you call east, what phase you call start, are often just that, choices. Now, here's the quiet twist. Nature doesn't just allow us to choose labels globally once for the whole universe. In many cases, the laws still work even if you're allowed to choose those labels locally, point by point, like a gentle freedom built into reality. And the moment you allow local freedom, something new is required. Imagine you and a friend are walking through a city using two different maps. You both agree on landmarks and streets, but your map is rotated slightly compared to theirs. If you stay close together, you can still coordinate. But as you wander, the mismatch starts to matter. You need a way to translate between your labels and their labels at each spot along the path. Something has to keep track of the changing relationship between two equally valid descriptions. That something is the spirit of a gauge field. A gauge field is not introduced because physicists love extra ingredients. It's introduced because the universe allows a kind of local bookkeeping freedom, and bookkeeping requires a keeper. So, in the gauge view of forces, the force field isn't an afterthought. It's the price of admission for local symmetry. Electromagnetism is the cleanest place to feel this. The electron is described by a field, an electron field spread through space, able to ripple and behave in ways that look like particles when excited. But it also has an internal rhythm, a kind of phase, like a wave where you start counting the cycle can be chosen. If you change that phase everywhere by the same amount, nothing physical changes. That's a symmetry. Now let that phase choice vary from place to place, like different clocks in different towns setting their zero slightly differently. Suddenly, if you try to compare an electron field here to an electron field over there, you need a rule for how to translate that local choice as you move. Otherwise, the theory becomes inconsistent, like trying to keep a melody steady while every musician silently redefines where the beat starts. The gauge field is the rule that keeps the melody coherent. And when that rule becomes dynamic, able to carry changes, able to ripple, able to store and release energy, it stops being a mere accounting trick and becomes something with physical presence. The electromagnetic gauge field is what we usually call the electromagnetic field itself. The ripples in that field are photons, so there's a softer way to say it. Matter fields are like instruments. Gauge fields are like the invisible agreement that lets the instruments stay in harmony across the whole orchestra, even if each player is allowed a tiny local freedom in how they count the beat. When that agreement flexes and travels, it becomes a real wave you can detect, light. This is why you'll sometimes hear physicists say that forces are the result of symmetry. It's not poetry, it's structure. If you demand local symmetry, local freedom to choose the internal labels, then the theory naturally calls for a companion field that connects those choices from point to point. That connecting field is what we experience as an interaction. And the word gauge itself is a hint. A gauge is something you can set to 0. You can reset it. You can choose a reference. Yet the physical readings, differences, changes, curvatures still matter. The gauge field carries what's needed so that changing your reference doesn't change the physics. Once you've seen that, it's easier to accept something that might have felt strange before. Electromagnetism isn't electric stuff floating around in space. It's a field that exists because the electron field has a local symmetry built into it. And the universe insists that symmetry remain true everywhere, not just in one perfectly chosen coordinate system. And electromagnetism is only the beginning. In the modern picture, there are other gauge fields too. The weak interaction has its own gauge fields. The strong interaction, the one that binds quarks inside protons and neutrons, has its own as well. They are different flavors of the same deep idea. Local symmetry needs a connector, and the connector behaves like a force-carrying field. Even if you never memorize the names, the feeling is enough. What we call forces may be the universe's way of keeping its descriptions consistent everywhere, all at once. Now, if that's true, if interactions can arise from symmetry and its companion fields, there's a natural question that appears almost on its own. Electromagnetism can bend a trajectory. The strong force can glue quarks together. The weak force can transform particles. But none of that, by itself, answers the quiet puzzle of weight and inertia. Why some fields behave as though they have mass while others glide effortlessly, like light. And that question leads us toward another field, one that doesn't just connect labels, but changes how certain particles move through the universe at all. Sometimes the biggest questions in physics arrive in the quietest way. If everything is fields, if forces are really fields talking to each other, then we're left with a simple, almost childlike puzzle. Why do some particles move through the universe as if they're heavy, while others glide along like pure light? We can feel mass in our everyday lives. It's the stubbornness of a grocery bag when you lift it. It's the way a bicycle slows when you stop pedaling. It's the reason planets hold on to moons, and why your feet stay friendly with the floor. But in the language of fundamental physics, mass isn't just a label you attach to an object. It's a relationship. It tells you how a particle responds when you push it, how it carries energy, how it curves a path, how it resists change. So, where does that relationship come from? For a long time, the story of mass was messy. Equations could describe particles with mass, sure, but the deeper you went into the clean, symmetrical world of fields, the harder it became to explain mass without breaking the very rules that made the theory work. Then came a strange, elegant idea. What if empty space isn't merely a stage where particles perform? What if space itself contains a kind of background field, quiet, steady, everywhere, so ordinary that we don't notice it, and yet so powerful that it changes how certain particles behave simply by being there? That's the Higgs field. The calm way to imagine it is not as a substance sloshing around, but as a fact about the vacuum, a field that, even in its lowest energy state, does not drop to zero. It has a non-zero value everywhere, like a gentle baseline threaded through the entire universe. And here's the key. Particles are not little marbles traveling through nothingness. They are ripples, excitations of their own fields. So the question becomes, how do those ripples relate to the Higgs field that fills space? Some ripples interact with it strongly. Some barely interact at all. That difference shows up to us as mass. If you want a soft mental picture, think of it like this. Two people walk across the same room. One moves easily, as if nothing tugs at them. The other keeps getting slowed, not by friction with the floor, but by constant tiny interactions, little exchanges that make their motion feel more reluctant. The Higgs field is not literally a sticky syrup, and mass is not literally drag, but the feeling of reluctance is a good emotional clue. In quantum field theory, mass can be understood as a kind of built-in coupling, an interaction that makes a particle's energy behave as if it has a resting weight even when it's not moving. And the Higgs story does something even more subtle than giving certain particles mass. It protects the whole structure of the theory. Because the standard model is built on symmetries, beautiful, strict rules about how fields transform. Those symmetries aren't just decoration. They're what keep the mathematics consistent and the predictions reliable. But there's a complication. The carriers of the weak force, those gauge fields, cannot behave the way we observe if they are massless. The weak force is short range. It doesn't reach across the solar system the way electromagnetism does. Something about it is heavier, more confined, more quickly fading. How do you give the weak force carriers mass without destroying the symmetry that holds the theory together? The Higgs mechanism is the trick. Not a trick like a cheat, more like a lock that opens when you turn the right key. The basic idea is that the equations can still be symmetric, while the vacuum, the lowest energy state of the fields, does not look symmetric. Physicists call this spontaneous symmetry breaking, but you can think of it as the universe choosing a particular quiet arrangement. The way a perfectly balanced pencil might fall in one direction, even though all directions were allowed. The rules stay the same. The resting state picks a preference, and once the vacuum has that preference, once the Higgs field settles into its non-zero baseline, the weak force gauge fields interact with it in a way that makes them behave as if they have mass. In practical terms, the W and Z bosons become heavy, and the weak force becomes short range, like a whisper that fades quickly. Meanwhile, the photon, the carrier of electromagnetism, stays massless. That contrast is one of the most satisfying parts of the whole story. The same field-based framework can produce both a long-range force of light and a short-range force of radioactivity, simply because of how the underlying fields couple to the Higgs background. And what about electrons and quarks, the matter particles themselves? They also have relationships with the Higgs field. Their masses depend on how strongly they couple to it. In the standard model, those couplings are built into the theory as numbers we measure. An electron couples weakly, so it's light. A top quark couples strongly, so it's heavy. The Higgs field doesn't decide their masses with personality or intention. It's more like a dial in nature's circuitry that sets how much a field's ripple feels the Higgs baseline. One important gentle correction here. The Higgs field is not the source of all mass in the universe. Most of the mass of everyday matter, like protons and neutrons, comes not from the Higgs directly, but from the energy of the strong force binding quarks together. It's field energy, trapped and shaped, showing up as mass through Einstein's familiar relationship between mass and energy. So, the Higgs isn't the entire story, but it is a crucial chapter. It explains why fundamental particles can have their own intrinsic masses while keeping the theory consistent, predictive, and deeply symmetric underneath. Now, every field we've talked about has a way to show itself. A field can be calm and invisible until you give it enough energy to ripple. The Higgs field is no exception. If the Higgs field is truly real, not just a mathematical convenience, then it should have an excitation, a ripple of the Higgs field itself. That ripple is the Higgs boson. When scientists finally observed it, it wasn't like seeing a tiny glowing bead. It was more like noticing a particular pattern in the way energy breaks apart, like recognizing a song from a few notes, heard through a wall, subtle, statistical, precise. And the reason it mattered wasn't just the headline. It was the feeling that a missing piece had clicked into place, the idea that the vacuum has structure, that empty space carries a quiet field, and that this field shapes the behavior of the particles that make up everything we touch. And that invites one last thought before we widen the lens. If the Higgs field is part of the vacuum's fabric, then the early universe, hotter, denser, more energetic, may not have looked the way it does now. The vacuum itself may have behaved differently. The baseline could have shifted. The rules might have been the same, while the resting state was not. Which means the story of fields is also a story of time, of a young universe where tiny ripples mattered, where background conditions shaped what could exist, and where the faintest fluctuations, once stretched and cooled, could become the seeds of everything that later learned how to shine. Picture the universe before it had anything like sky or space the way we know it. Not empty, not quiet, not cold. More like an ocean of energy, so hot and dense that the usual categories of things don't quite fit. There aren't planets yet, no atoms, no light traveling freely for billions of years. Just a young cosmos, packed tight, with fields everywhere and energy moving through them like a restless tide. And in that early time, the most important events are not the dramatic ones. They're the tiny ones, because the universe didn't start perfectly smooth. Even in its earliest moments, it had faint unevenness, microscopic variations, barely there. If you could somehow hover above that newborn sea, you wouldn't see mountains or storms. You'd see a surface that looks almost level, except for the slightest shimmer, the kind of shimmer you notice only when you stop trying to notice and let your eyes soften. Those faint variations are what we call fluctuations. And the strange, beautiful point is that these fluctuations weren't just noise. They weren't an accident of messy conditions. In the quantum picture, a completely featureless, perfectly still state is not really an option. Fields have a kind of unavoidable restlessness built into them. Not loud restlessness, more like the gentle tremble of a hand trying to hold perfectly still. The baseline is never a hard flat line. There is always a little texture in the fabric. In the early universe, that texture mattered, because gravity is patient. Gravity doesn't need big differences to begin its work. It only needs a slight imbalance, one region just a little denser than another, one patch with a tiny extra pull. Over time, that slightly denser patch tugs on its surroundings. It gathers more. It becomes denser still. And the process repeats, slowly at first, and then more eagerly. It's a soft idea to hold. The largest structures in the universe may have begun as the smallest imperfections. Now, early on, the universe isn't made of separate calm ingredients. Matter and light are tightly coupled, almost like dance partners who can't let go. Photons are constantly scattering off charged particles, especially electrons. That means light can't simply stream away into the distance. It's trapped in a thick fog, bouncing and rebouncing, sharing its energy with everything around it. So the young universe behaves less like empty space and more like a glowing fluid. In that fluid, fluctuations don't grow in a simple straight line. Gravity tries to pull material inward, but radiation pressure pushes back outward. The result is a kind of cosmic ringing, gentle compression and rarefaction, like sound waves moving through a medium. Not sound you could hear in the usual way, but the same basic pattern, a push and a pull, a squeeze and a release. Those waves leave fingerprints. Much later, we would detect echoes of them as subtle patterns in the cosmic microwave background, the faint afterglow of the early universe. And we would see their influence in the distribution of galaxies across space, as if the universe remembers the rhythm of its infancy. But the deeper story is still the same. Small differences become guiding lines. There's another quiet player here that doesn't get enough credit in the bedtime version of this tale: dark matter. We don't see it directly, but it behaves as if it's there, adding gravity without adding light. And because it doesn't interact with light the way normal matter does, it can begin clumping earlier without being held back by that photon fog. It starts building a kind of invisible scaffolding, an outline of future structure. Normal matter, the kind that will one day become atoms and oceans and pine trees, eventually falls into that scaffolding. It collects in the gravitational valleys dark matter helps carve. So, when we say tiny fluctuations became galaxies, we don't mean a galaxy popped out of a ripple like a magician's trick. We mean that, over long spans of time, the universe allowed gravity to read those ripples, turning faint statistical texture into actual architecture. Eventually, the universe cools enough for a major shift. Electrons and protons can finally settle into stable atoms. When that happens, photons suddenly stop bouncing so often. The fog lifts, light is free to travel, space becomes transparent. That moment is one of the most poetic transitions in all of cosmology. The universe goes from opaque to clear, like a window wiped clean for the first time. And those freed photons are still with us, stretched by expansion into microwaves, filling the cosmos as a cold, gentle background glow. But the story doesn't end at transparency. In some ways, it begins there. Because once matter can move without being constantly shoved around by radiation, gravity can work more efficiently. Over hundreds of millions of years, the densest regions become denser, the first stars ignite, the first galaxies assemble. Over time, clusters form, and filaments, long cosmic strands, connect them. Vast voids open up in between, like quiet valleys between mountain ranges. If you zoom far enough out, the universe begins to look like a web. And that web is the grown-up version of those earliest ripples. So, when you picture the early universe, try not to imagine a clean blank canvas that later gets painted. Imagine a canvas that already has a faint grain in it, so subtle you might miss it unless you tilt it in the light. And then imagine time, gravity, and expansion slowly bringing that grain into focus until it becomes the largest pattern there is. It's a comforting thought, in a way. It suggests that complexity doesn't always need a grand plan. Sometimes it begins with the smallest unevenness, patiently magnified by simple rules. And it also sets the stage for the next idea, the one that makes this story feel almost unbelievable. The possibility that the early universe didn't just expand. It may have expanded in a sudden, extraordinary surge, stretching those tiny quantum ripples across enormous distances, like ink pulled into delicate threads. Not a loud explosion, more like a breath, vast, fast, and quietly decisive, leaving behind a universe with seeds already planted, waiting to grow. Imagine the universe when it was still impossibly young, so young that time itself feels like a word that doesn't quite fit. Not because nothing existed, but because everything that did exist was packed into a state so hot, so dense, and so energetic that the very idea of space had barely begun to feel roomy. In that newborn cosmos, the quantum fields were already there, quietly present in the way fields always are. And even in their lowest, calmest states, they weren't perfectly still. There were tiny ripples, tiny jitters, little unevennesses that were not mistakes or clutter, but simply the natural texture of a quantum world. Now here's the strange, almost poetic twist. Those tiny ripples were unbelievably small. So small that, in a normal, everyday sense, you'd never think they could matter. And yet, modern cosmology tells a story where those almost invisible wiggles may have been stretched into the largest patterns we can see in the entire sky. That stretching is what people are pointing to when they talk about inflation. Inflation is the idea that, very early on, the universe went through a brief episode of extremely rapid expansion, faster than you'd expect if you only imagine space growing the way a balloon gently inflates. The word rapid here doesn't mean like a firework you could watch. It means rapid on a cosmic scale, in an era when the universe was already racing through changes that don't have any everyday comparison. A soft way to picture it is to think of space like fabric, not a fabric sitting inside something else. Space isn't laid out on a table, it's the fabric itself. Inflation is the suggestion that this fabric suddenly began to stretch enormously, smoothing and expanding everything at once. And if space stretches, it carries patterns with it. If you had a microscopic ripple, something so small it could fit inside a region smaller than an atom, stretching space could pull that ripple outward, widening it into a larger and larger wave, not making it louder necessarily, just making its scale bigger, like drawing a tiny squiggle on a rubber sheet, and then pulling the sheet tight until the squiggle spans the whole surface. This matters because we look out at the universe and see a kind of faint, ancient fingerprint. The cosmic microwave background, a glow left over from the early universe. It isn't perfectly uniform. It has tiny variations, slightly warmer spots, slightly cooler spots, like a soft modeling across the sky. And those variations line up beautifully with the idea that the early universe contained small fluctuations that later became the seeds of everything: stars, galaxies, clusters, and the web-like structure of matter spread across billions of light years. Inflation also tries to answer a few quiet puzzles that used to feel unsettling. One is this "why does the universe look so even?" question. When we look in opposite directions across the sky, those regions look remarkably similar in temperature. In a simple picture without inflation, it's hard to see how far apart regions could have shared information or come to the same temperature, because light and anything that carries cause and effect only travels so fast. Inflation suggests that those regions were once much closer together, able to settle into similar conditions before expansion pulled them far apart. Another is the "why is space so close to flat?" question. On enormous scales, the geometry of the universe appears to be very nearly flat, not curved dramatically one way or the other. Inflation naturally pushes things toward flatness, the way stretching a wrinkled surface makes it look smoother and straighter over large distances. There's also a more technical missing relics question that inflation can help with, involving exotic leftovers that certain early universe theories might predict. Inflation, by expanding space so drastically, could dilute those leftovers until they become extraordinarily rare enough that it's no longer surprising we don't see them easily. So, inflation is not just a dramatic flourish. It's a way of making the early universe's story feel more coherent, more like a single unfolding narrative rather than a set of coincidences. But there's an important gentle honesty to keep here. Inflation is a leading idea, not a final closed case. Scientists have strong reasons to take it seriously, and it fits a lot of the data beautifully. Yet the exact mechanism, what field drove inflation, how it began, how it ended, and what it precisely predicts in every detail, is still an area of active research. In some versions of the story, inflation is powered by a special field. In others, it emerges from deeper physics we're still trying to understand. The universe, as always, is generous with clues and stingy with final answers. Still, even as an idea, inflation does something wonderful for our theme tonight. It ties the tiny and the enormous together. It suggests that the delicate quantum texture of reality, those soft fluctuations we talked about, didn't stay trapped in the microscopic world. Instead, the universe may have taken those faint tremors and stretched them outward, like turning a whisper into a landscape. The galaxies become, in a sense, the slow-motion aftermath of a very early quantum murmur. And if that's true, it means the large-scale structure of the cosmos is not separate from quantum fields. It is, at least partly, a memory of them, a record written in the distribution of matter and light across the sky. Which brings us to a quiet, lingering question. If the universe once expanded in this extraordinary way, why is it expanding the way it is now? Because today, the expansion seems to be accelerating again, much later, much calmer, but still with a mysterious push behind it. And that's where the conversation naturally drifts toward an even stranger phrase: vacuum energy, and the puzzle we call dark energy. There's a moment in this story where the universe feels almost like it's teasing us. Because once you accept the idea of quantum fields, present everywhere, even when nothing seems to be happening, you naturally start to wonder about the quietest thing a field can be, its baseline, its lowest possible energy, the vacuum state. And then you realize something unsettling in the gentlest possible way. If the vacuum is the lowest energy state, and if that state still contains a faint, restless quantum texture, then the vacuum is not just empty, it's something. And in physics, something usually has consequences. Here's the simplest way to hold it in your mind. Imagine the universe as a vast ocean made of fields. Most of the time, we talk about the visible waves, the particles, the light, the matter, because those are the parts that sparkle. But the ocean also has a level, a background height, a baseline that's there even on the calmest night when the surface looks smooth from far away. In quantum field theory, that baseline is what we call vacuum energy, the energy associated with the vacuum state of fields. Now, a small but important detail. In everyday life, vacuum energy can sound like a magical battery, like a hidden power source you could plug into if you found the right wire. That's not what it means here. Vacuum energy, in the careful physics sense, isn't a free lunch you can scoop up. It's more like a background property of the fields themselves. It's not sitting in a tank waiting to be drained. It's part of how the universe is set up. And if it exists, gravity should care. Because in Einstein's picture, gravity doesn't only respond to mass in the old-fashioned sense. It responds to energy and pressure too. If the vacuum has an energy density, if there's a little background energy per volume in space, then, in principle, it could influence how space expands. This is where the conversation slides, almost inevitably, into one of the biggest mysteries in modern cosmology: dark energy. Dark energy is a name we give to whatever is causing the expansion of the universe to speed up over time, not slow down, as you might naively expect if gravity were the only major player. Speed up, like a car quietly rolling downhill, gaining momentum when you thought it should be coasting to a stop. The evidence for this accelerated expansion doesn't come from a single dramatic experiment. It comes from a steady convergence of measurements, different ways of looking at the cosmos that, together, keep pointing to the same conclusion. The universe's expansion history doesn't fit a simple, matter-only story. So, we introduce a new ingredient, a smooth, pervasive component that doesn't clump into stars or galaxies, but fills space more evenly. Something with a kind of gravitational effect that, on the largest scales, drives space to expand faster. We call it dark not because it's evil or spooky, but because it doesn't shine. It doesn't scatter light in an obvious way, and we can't hold it in our hands. We infer it through its influence on the geometry and expansion of the universe. Now comes the tempting leap. What if dark energy is vacuum energy? It sounds elegant, almost too elegant. The vacuum is everywhere. Dark energy seems to be everywhere. The vacuum has energy. Dark energy acts like an energy of space. It feels like two puzzle pieces that were meant to click together. And in some of the simplest models, that's exactly the idea. Dark energy behaves like a constant property of empty space, often called a cosmological constant. In that picture, the energy density of space stays roughly the same as the universe expands. As the universe grows, there's simply more space, and therefore more of this background energy in total. The effect becomes more noticeable as matter thins out over cosmic time. So far, it's a clean story. But then quantum field theory whispers something that turns the clean story into a paradox. When physicists do the most straightforward kind of calculation, adding up the expected contributions of quantum fluctuations to the vacuum energy, they tend to get an answer that is absurdly larger than what the universe's acceleration seems to allow. Not a little off, not we need better measurements, off by a staggering amount. This mismatch is often described as one of the worst prediction failures in physics, though it's not really a failure of quantum field theory's practical predictions. QFT works astonishingly well where we can test it in laboratories. It's more that when we try to marry QFT's idea of vacuum energy with gravity and the observed expansion of the universe, the numbers don't peacefully coexist. It's like having two maps that are both excellent in their own regions, but they don't line up at the border. This tension is called the cosmological constant problem, and it's one of those rare scientific puzzles that feels both technical and philosophical at once. It's technical because it lives in the details of quantum fields, energy scales, and gravity. And it's philosophical because it makes you ask, quietly, what are we missing about the vacuum, about space, about the way gravity reads energy? So, What are the possibilities? One possibility is that dark energy really is a cosmological constant, vacuum energy, but there's some mechanism we don't yet understand that makes the effective value tiny. In this view, the vacuum energy that matters for cosmic expansion is not the naive sum we write down, but something renormalized, canceled, balanced, or selected by deeper physics. Another possibility is that dark energy is not constant at all. Maybe it's a dynamic field, something that changes slowly over time, like a very gentle slope rather than a fixed floor. People sometimes call ideas like this quintessence. But you don't need the label. The core concept is simple. Instead of space having a permanent built-in energy, perhaps there's a field whose energy evolves, and the universe's expansion responds to it. A third possibility is even more radical. Perhaps our understanding of gravity on the largest scales is incomplete. Maybe the way space-time behaves across billions of light years isn't captured perfectly by the simplest equations we use. In that scenario, what we interpret as dark energy might be a sign that gravity itself needs an update. And then there's the most honest possibility of all. We don't yet know which story is true, and the universe hasn't handed us the final page. What we can say is that, observationally, dark energy looks smooth, subtle, and persistent. It doesn't form bright structures. It doesn't gather into clouds. It doesn't make a messy footprint the way matter does. It shows up as a gentle but relentless shaping of the cosmos's expansion, something you only notice when you compare very large distances and very long spans of time. So, in a way, this is the perfect topic for a slow, late-night kind of curiosity. Because dark energy is not a loud mystery, it's a quiet one. It's the kind of mystery you feel more than you see, the sense that space itself has a preference, that the universe, as it ages, is not merely coasting, it's leaning into expansion. And it brings us back softly to our main theme. Quantum field theory can be incredibly precise, almost shockingly successful, and still leave room for deep uncertainty and interpretation, especially when we push it into the largest, most extreme arena imaginable. Which raises a gentle question to carry forward. If our equations predict with breathtaking accuracy, yet the meaning of vacuum still slips through our fingers, what does that say about measurement and about what we call reality when everything is built from fields? After all the talk of vacuum energy and dark energy, after the uneasy feeling that our best guess and the universe's actual numbers don't quite shake hands, there's a quieter question waiting underneath it all. What exactly do we mean when we say a theory is true? In quantum field theory, the honest answer is surprisingly simple. A theory earns our trust when it predicts what our instruments will do, not what we wish the world were doing behind the scenes. Not what feels most intuitive in our minds, but what shows up as a pattern, again and again, when we build careful experiments and listen. If you've ever seen a picture of a particle detector, it can look almost theatrical, layers of metal and silicon and cables, all arranged like a high-tech onion. In the center, something happens, an interaction too small to witness directly. And outward from that center, the detector translates that event into traces. A tiny burst of light, a shift in voltage, a trail of ionized gas, a click in the most modern sense of the word. That's measurement in this world, not a human eye catching a glimpse, more like a conversation between fields and matter, where the detector is just another physical system built out of fields itself, responding the only way it can, by changing. And that's why quantum field theory can feel so grounded and so mysterious at the same time. Grounded because it's astonishingly good at predicting those responses. When you calculate how an electron should behave in an electromagnetic field, how it should scatter, how it should couple, how it should shift and wobble under the influence of vacuum fluctuations, the numbers you get aren't just pretty good. They can be almost embarrassingly precise. It's as if nature is whispering, yes, that's the rulebook. But mysterious, because the rulebook doesn't come with a single, universally agreed upon story about what's really happening between the clicks. Quantum field theory, at its heart, is a machine for producing probabilities. It tells you what outcomes are likely when a system is prepared in a certain way, and then allowed to interact with something else, like a detector or a beam splitter or another particle field. It gives you the odds of different results, and it gives them with incredible accuracy. Yet it leaves room for interpretation when you ask the more philosophical question: what is reality when we're not looking? Some people are perfectly comfortable with an answer that's almost Zen-like. Physics is about what we can say, not what we can imagine. The real content of the theory is the set of predictions and the rules for making them. If the theory tells you what a detector will register, and it keeps being right, then that's reality enough. Others want a picture that feels more continuous, something that doesn't leap from maybe to definitely the moment you read an instrument. And that's where different interpretations come in. They're not different versions of the math, not different equations competing in the same arena. They're different ways of telling the story that sits underneath the same successful predictions. One way to tell it is the old practical one. Before measurement, you don't assign a single, definite outcome. You assign a spread of possibilities. Then, when a measurement happens, when the system interacts strongly with the environment or a detector, you update your description to match what occurred. It's not necessarily a statement about human awareness. It's a statement about what happens when a delicate quantum system becomes tangled up with a large, messy, irreversible world. Another way to tell it leans on a quiet process called decoherence. It says, look, the universe doesn't need a magical moment of decision. Quantum systems are constantly interacting with their surroundings. Those surroundings, air molecules, thermal vibrations, stray photons, act like a vast, uninvited audience. Through those interactions, certain possibilities lose the ability to interfere with each other. The quantum weirdness doesn't vanish, but it becomes practically inaccessible, like a song drowned out by a crowd. The world starts to behave classical, not because the quantum rules stop, but because the interference that made them feel strange becomes impossible to track. Some people prefer a story where all outcomes exist in a larger structure, and measurement is simply the moment your experience becomes correlated with one branch of that structure. Others treat probabilities more like personal expectations, carefully updated beliefs about what you'll experience next, rather than objective physical fluids sloshing around. And there are still other frameworks that aim for consistency in what can be said about histories, or what can be known without contradiction. It can feel like too many stories for one set of equations. But here's the soothing part. These different stories mostly agree on what you will actually see. They live in the same neighborhood of predictions. And that's why physicists can argue about interpretation over coffee, then return to the lab and still build devices that work. Because quantum field theory is not shy about being useful. It tells you how the electromagnetic field and the electron field interact. It tells you what kinds of excitations can be created, how they can scatter, how they can decay, and what patterns will appear when you measure the aftermath. It does this without requiring you to settle the deepest metaphysical question first. In a way, QFT is almost humble. It says, here is how nature behaves when fields talk to fields. Here is the probability of each answer the universe might give you when you ask it a question with an experiment. And then it steps back. So, when you hear someone say, quantum field theory describes reality, it's worth hearing the gentle nuance behind it. QFT describes reality in the way a map describes a landscape. A good map doesn't have to settle philosophical debates about what a mountain really is. It only has to reliably guide you from one place to another. It has to match the contours that matter. It has to predict what you'll encounter when you walk. Quantum field theory is a map like that, except the landscape is made of interactions, and the roads are probabilities, and the landmarks are the readings our instruments return to us. And there's another quiet twist here too. In the field picture, measurement isn't something that happens outside physics. It's not an extra rule stapled on at the end. A detector is made of atoms, Atoms are made of fields and bound, structured arrangements. The act of measuring is itself an interaction between fields, an event in the same universe, under the same laws. Which means the line between system and observer is less like a wall and more like a practical boundary we draw to do calculations. We decide what we're focusing on and what we're treating as the environment. The universe itself doesn't care about our bookkeeping, it just keeps interacting. And once you let that sink in, the question, is the quantum field real, becomes less dramatic and more peaceful. Real in the sense that it does things. Real in the sense that it leaves footprints in our devices. Real in the sense that we can rely on it to predict outcomes so precisely that modern life has been built on those predictions. But also, still mysterious in the sense that our favorite human stories may never completely capture what it is in the quiet spaces between events. And maybe that's okay. Maybe, for tonight, it's enough to hold both truths gently. The predictions are rock solid, and the interpretation is still a little like starlight, clear, beautiful, and not fully grasped in the hand. Because the funny thing is, you're not just thinking about quantum fields from a distance. You're resting inside them. And in a moment, we can let that thought drift into something surprisingly practical. How this invisible, mathematical-looking framework quietly powers the everyday devices all around you, from the screen you're watching to the tiniest switches inside a chip. It's easy to let quantum fields stay out there in the textbook universe. Shimmering diagrams, chalk dust, distant laboratories. But the quietly funny truth is that you've been living inside field physics all day long without ever needing to call it that. Start with the simplest, most ordinary thing you might have within reach. Your phone, a laptop, a little smart speaker, a bedside clock with a glowing display. None of these are quantum toys. They're just normal, and yet inside every one of them, electrons are behaving in a way that only makes sense if you treat matter as something more than a handful of tiny marbles bouncing around. A transistor, this humble switch that sits at the heart of modern electronics, works because electrons don't have permission to do just anything they want. In solids, they fall into patterns. They organize into energy ranges they can occupy and ranges they can't. Those allowed and forbidden places are not just engineering jargon, they're a fingerprint of quantum rules. When engineers shape silicon with tiny impurities, they're not merely adding material, they're gently rearranging what kinds of electron states the material makes available, like tuning the keys on a piano so certain notes become easy to play, and others become nearly impossible. So, when a chip flips between a 0 and a 1, it isn't only a mechanical action, it's a quiet negotiation with the underlying fields. Electrons in a crystal responding to electric forces, settling into stable patterns, refusing certain moves, accepting others, all with a reliability that feels almost mundane. That reliability is the miracle, not that it's mystical, but that the universe offers rules you can count on, billions of times per second. Light too shows up in your daily life with a kind of gentle precision that would be impossible without quantum ideas. A laser is a good example, not because it's flashy, but because it's disciplined. Ordinary light from a bulb is like a crowd. Many colors, many phases, many little waves stepping on one another's toes. Laser light is like a choir that somehow agrees, breath after breath, to sing the same note in step. That agreement happens because atoms and electrons have quantized ways of giving off energy. They don't slide down a smooth ramp. They drop in discrete transitions. The laser is what you get when you build a careful environment that encourages those transitions to happen in harmony. And then the laser stops being a laboratory curiosity and becomes everything. Barcode scanners, fiber optic internet, eye surgery, tiny pointers, the calm red dot on a wall, the invisible streams of light that carry your messages across oceans. The field story is the same, an electromagnetic field that can be excited in a controlled way, with matter responding to quantum constraints, and even the gentle glow of an LED, so common you barely notice it, belongs to this same family. that soft blue on a charger, the warm amber in a lamp, the crisp white in a streetlight. Each color is a little statement about energy differences inside a material. The material decides what energies are allowed, and the light that comes out is the difference, translated into color. When you see an LED shining, you're watching a microscopic accounting of energy being balanced, one tiny packet at a time. If you've ever had an MRI scan, you've stepped into a technology that's practically a lullaby of field interactions. Strong magnetic fields, carefully timed radio pulses, and the quiet response of atomic nuclei. Inside your body, certain particles behave like tiny magnets. In an MRI machine, they align and wobble in a predictable way, like slow compass needles in a very controlled storm. That predictability lets us build images, not by cutting or invading, but by listening, by coaxing matter to respond, and then reading the response. It's one of the most peaceful uses of deep physics. A conversation with the body using fields and timing. Even time itself, your most familiar companion, gets its modern sharpness from quantum behavior. Atomic clocks work because atoms have extremely specific transition frequencies. They are nature's metronomes. They tick not because someone wound them up, but because the universe provides stable steps between energy states. When your phone updates the time, or a GPS system coordinates signals from satellites, it leans on clocks whose steadiness comes from quantum rules, playing out with astonishing consistency. And GPS, in its own quiet way, is one of the greatest everyday demonstrations that physics is not abstract. The location dots on a map depends on signals traveling at the speed of light, on precise timing, on predictable behavior of atoms, and on a world where electromagnetic fields do exactly what our equations say they will do. It's not that you need to understand every layer to appreciate it. It's simply worth noticing that the universe allows precision at all. Once you start looking, you see this pattern everywhere. Solar panels turning sunlight into current, sensors and cameras converting light into charge, superconducting devices in medical imaging and research, the electronics that control planes, cars, and power grids. Each one is an agreement between human design and natural law. We build the stage. The fields do what fields do. And that's the gentle punchline. Quantum field theory isn't only a philosophical story about what's real. It's also a practical language for why the modern world behaves as reliably as it does. We don't need the universe to be intuitive. We need it to be consistent. And it is, in a way that's almost soothing, which makes it a good moment to do something simple and kind, to clear away a few common misunderstandings that tend to gather around these ideas, like dust around a bright lamp. There are a few myths that cling to the phrase quantum vacuum, the way fog clings to a quiet streetlight, and none of them are anyone's fault. The words sound like they're pointing to magic. So, let's tidy up 3 of the most common misunderstandings, gently, without scolding, and without turning this into a lecture. The first myth is the tempting one. If empty space has energy, then maybe it's an endless battery. The idea shows up in headlines and sci-fi stories all the time. Vacuum energy as a cosmic power outlet, just waiting for the right plug. But in physics, energy in the vacuum doesn't mean energy you can freely siphon. It means the fields have a lowest energy state, and that state isn't perfectly silent. The important word there is lowest. You can't extract useful work from something that's already at the bottom, any more than you can drain a lake that's level with the sea. You can observe differences and you can see effects when conditions change, like boundaries, materials, or geometry. But that's not the same as a free, limitless fuel source. The vacuum isn't a hidden stash of gasoline. It's more like the quiet hum of a refrigerator in the next room. Real, measurable if you're careful, but not something you can turn into unlimited motion without paying a cost somewhere else. The second myth is about virtual particles. People hear the phrase and imagine tiny ghost bees constantly popping in and out of existence, swarming through space like an invisible storm. It makes for a vivid picture, but it can lead you in the wrong direction. virtual particle is mostly a bookkeeping word, a convenient way of describing how fields interact when you do the math. It's less like a camera catching literal creatures, and more like a map's contour lines. The lines help you calculate the shape of a hill, but the hill isn't made of ink. In the same way, virtual particles aren't little pellets flying around inside the vacuum like secret fireworks. They're a way of representing the push and pull, how one field's ripples can influence another field's ripples. The interactions are real. The particle picture is often a helpful language for the calculation, not a tiny documentary of what's physically zipping through space. And the third myth sounds old-fashioned on purpose. A field is just the ether with a new name. In the 1800s, people imagined light waves must travel through a special substance, an ether filling all of space. That idea didn't survive the way experiments turned out, and modern physics moved on. A field is not a material medium like air or water. It's not a preferred stuff that says the universe has a special rest frame. A field is a physical quantity assigned everywhere, a real feature of nature that can store energy, carry momentum, and respond to forces without being a hidden fluid sloshing behind reality. The field isn't a stage curtain, it's part of the stage itself, described in a way that still respects the deep rules we've learned. No special direction, no universal, you're standing still right here, sign posted in the cosmos. So, if you hold on to just one gentle takeaway, let it be this. Quantum fields aren't magic, and they aren't metaphors. They're a remarkably accurate way of describing what the universe is doing, quietly, consistently, even when we call it empty. And with those myths set down softly, we can let our curiosity drift forward again, toward the open questions that remain, like slow clouds crossing a moonlit sky. There are a few questions that sit at the very edge of this story, quiet questions that don't demand answers tonight, but still have a way of glowing in the mind like distant lights across a dark horizon. One of them is about gravity. Quantum field theory is astonishingly precise when it comes to the world of particles and forces we can measure in laboratories. And gravity is astonishingly reliable when it comes to shaping planets, stars, and the large-scale architecture of the cosmos. But when you try to describe places where gravity becomes extreme, near the center of a black hole, or in the earliest instance of the universe, the two descriptions don't settle into a single smooth picture. So, the question becomes simple to say and very hard to finish. What happens when quantum fields and gravity have to speak the same language? Another question is even softer, almost philosophical in the gentlest way. We have been talking as if fields live in space, as if space is the stage, and fields are what perform on it. But some ideas in modern physics suggest the stage might not be fundamental. Space and time themselves may be something that emerges from deeper rules, something that appears only when you zoom out, the way a coastline appears from far above, even though it's made from countless tiny details. So the question turns into a whisper. Is space-time itself a kind of field, or the result of fields we haven't yet learned to see? And then there's the question that circles back to the strange heart of emptiness. If the vacuum isn't truly empty, if it still contains the quiet presence of fields, then it should have an energy. In fact, naively, it should have an enormous energy. And yet the universe seems to be expanding with a gentle acceleration, as if the vacuum energy we observe is small, mysteriously small. So the last question is almost poetic. Why is the vacuum so quiet? You don't need to solve any of these tonight. You can simply let them drift, like slow clouds passing through a wide, star-filled sky. While the deeper parts of your mind do what they've always done, hold wonder without forcing it into a conclusion. And now, you don't have to hold any of this tightly. You can let the ideas loosen, the way a hand relaxes when it stops trying to grip water. Somewhere beyond your walls, the universe keeps doing what it has always done. Quiet fields stretching through the dark, rippling softly, trading whispers of energy back and forth, not as a performance, not for an audience, just as nature's steady way of being. If you picture it simply. a vast night ocean made of fields, almost still, and you, right where you are, like a small, warm boat that doesn't need to row. You're allowed to float. You're allowed to be carried by the gentle motion without solving anything, without chasing the final answer. Because the comfort of this story isn't that we've pinned reality down. It's that reality is consistent, patient enough to be measured, and mysterious enough to stay interesting, even at a whisper. Thank you for spending this time with me, for bringing your attention to something so strange and so beautiful, and letting it become calm instead of loud. If this kind of slow, cozy science helps you unwind, you can leave a like or subscribe. It truly helps this little channel find the people who need it. And if you feel like it, tell me where you're listening from tonight. Good night, and thank you for drifting with me.